welcome to the ITC Colloquium. Today we are delighted to welcome Professor Chris Kochanek, who is a professor at Ohio State University. He did his PhD in Caltech in 1989, and then was a postdoc at Berkeley before joining here as a junior faculty at Harvard, and then a senior scientist at the CFA, and now is a professor and Ohio Eminent Scholar faculty at Ohio State University since 2003. So his research interests include cosmology, gravitational lensing, and mainly supernovae. And he's part of the Assassin All-Sky Automated Survey to find transients daily. Now today he'll be talking about failed supernovae, and welcome to it.
Okay, so probably you've all been doing your undergraduate astronomy courses and lying to all of the students that you tell them that massive stars are supposed to explode, whereas in fact you actually have a very limited basis for actually believing that to be the case. We know some of them explode, but we really don't have a good idea of what that fraction is. And there's good reasons to think that a significant fraction of them in fact do not explode. And so the question then becomes is, well, how can you find things which don't explode? And it turns out you can do that. And we actually have a candidate, so I'm going to go through this story. And so what we want is to ban this. Okay, this is of course 87A, which is the nearest supernova. And probably about as close as you can put a supernova where you might be able to find the formation of a failed supernova using LIGO.
Is it possible with the superconducting content? Would we have found the neutrinos for such things?
So neutrinos could also do it out to the LMC, but not to M31. Even hyper K, if they build it, would have trouble with M31. Okay, so let's do some context on supernova. All right, so we're talking about core collapse supernova, not the thermonuclear kind. And this is driven by the buildup of an iron core, which becomes unstable. The core collapses, and in some cases drives a supernova explosion, which then has some set of astronomical classifications basically based on spectroscopy. And the differences between the various types is basically interpreted as degrees of mass loss. That mass loss could be either due to winds or due to binary interactions. It's a very interesting problem at the moment as to how much of the properties of supernova are driven by binaries. And of course, the fundamental problem with supernova is they're absolutely horrible at producing light. I mean, they're the world's most inefficient ways of generating visible light, because 99% of the energy is neutrinos, 1% is about kinetic energy, and about 10% of that actually comes out of light. And so they're actually absolutely horrible at producing any radiation. Okay, so all stars above about 8 times the mass of the sun must undergo core collapse. So that part at least is fairly unambiguous. Is in the last few days, you burn the core from silicon to iron. The iron builds up to, it's not really the Chandrasekhar mass, but 1 to 2 times the mass of the sun, and it collapses. There's no observational requirement that more than 50%-ish of core collapses become supernova. And the ways you can try to do this are, you can look for the diffuse neutrino background, right? Because even the ones which are failed supernova would contribute to the diffuse neutrino background. This likely is going to be solved pretty clearly by the upgrade of Super K to spike it with gadolinium. And the cleaned up Super K should be able to measure the diffuse neutrino background rather than just set a limit on it. And so they are about to do that. You can try to compare the star formation rate to the supernova rate. Again, you won't trust this to a factor of 2, but they agree to about a factor of 2. And you can ask, well, if I just start chopping out bits of the massive stars and ask what happens to nuclear synthesis, you can chop out about half of the stars, and you can still make all the nucleosynthetic yields constraints work fine. Okay, so what happens? You have a core which is roughly the size of the Earth. It collapses down to about 100 kilometers or so. At that point, the strong nuclear force becomes important and repulsive. The core stops, bounces a little bit. That drives a shock wave out. The shock wave always stalls. So the shock waves goes out to a few hundred kilometers per second and hangs up. And so this was the original idea about how to blow up the stars, and it turned out it just didn't work. And so you have to somehow revive the shock. If you could revive the shock and get it to the surface, you get a supernova. If you expel all of the mass, you'll get a neutron star. If you can somehow very finely tune the explosion so that some of the mass falls back, you might get what's called a fallback black hole formed. Or the shock fails, in which case there is no dramatic supernova explosion, and you have to end up a black hole. So once it was realized that the basic bounce didn't work, people worked on this for a while and eventually came up with the neutrino mechanism, where almost all of the energy is in neutrinos, and while neutrinos are weakly interacting is not non-interacting. And so if you can tap a small amount of the energy in the neutrinos, you can try to revive the shock wave and drive the explosion. Except for the low mass stars, down around 10 solar masses, the neutrino mechanism pretty robustly works. But as you go up even to 11, 12 solar masses, it doesn't work in one dimension. That it generically fails for spherical stars. It's basically that the neutrino luminosity ends up just being a little bit too low for the more massive stars. And so for the last 30-odd years, people have been hoping that somehow getting out of spherical symmetry would solve the problem. Initially there was a lot of excitement because in 2D suddenly stars became easier to explode. On the other hand, is if you just look at the simulations, right, you see a characteristic structure which is sort of characteristic of turbulence in 2D, that everything goes up to very big structures. And it's not too surprising that if you put everything into very big structures, it's easier to explode, except you then turn around and say, yeah, but if I do this in 3D, turbulence goes the other direction. And so when they went to 3D, they in fact found that the stars became harder to explode.
But string theorists say that we are in T10.
Well, the supernova aren't. And so people are still working on it, and still the hope is that somehow the dimensionality can help drive the explosions. But there's a fundamental problem, is if you go to Adam Burrows and hand him your 15 solar mass star, right, Adam is basically sitting there and he is going to work until he makes that star explode. Except, how does he know that was the right answer? Right? There's no a priori reason that says that a 15 solar mass star should explode. And so it's not clear whether he's working towards the right outcome in trying to make that star explode. So there have been a lot of recent studies of the explodability of stars. And so while you can't, the theory is not robust enough to simply say, here is the results, you can ask, is a star easier or harder to explode? And a simple way of characterizing this is what's called the compactness. Is you take some mass cut, like 2 solar masses, and you divide it by the radius enclosing that 2 solar masses, or 2.5 solar masses. And so here, for 2 different models, is a function of progenitor mass, this compactness. And basically what happens is that the compactness is higher, the star is more difficult to explode. And the way to think about it is that what is preventing the shock from going outwards? What's preventing the shock from going outwards is the ram pressure of the infalling envelope. And so depending on the core structure, that ram pressure can be either higher or lower. And if the ram pressure is high, it's hard to explode the star. If the ram pressure is low, it's easier to explode the star. And so here you see these ones down around 10 solar masses, the compactness is quite low. And these are the ones that robustly blow up, even in 1D with the neutrino mechanism. You can see there then has this very complicated structure. And in fact, there's even more substructure than that. T. Suckbold has a sort of very long paper explaining why there's a lot of structure that's coming from interactions of shell burning phases once you're burning carbon. But you can see there's a peak. There actually is a peak in here at around 15 solar masses, which is one reason I'm teasing Adam Burrows in absentia, is that in fact it turns out that 15 solar masses is one that's hard to explode. Then there's this peak around 20, 25 solar masses, and then up around 40. Okay, but it's a very complicated function of mass.
Where would you put 87A?
87A is around 18. It would actually sit in a gap. There's a peak at 15 and it goes down
It's
again.
in the bottom there.
Yeah.
Okay. No, but 18, is it the progenitor mass or the pre-explosion mass?
So this is all done in SAM's mass, which for 87A is problematic since it's probably a merger as well.
Well, that's the thing. If you have a binary, then it's changed.
Right.
Yeah.
Okay, good.
This is all single star. So, I mean, part of the problem is it is difficult even if you want to do a merger scenario for how you construct the star post-merger. There's actually very little work on how you go from merger to the next thing other than these sort of entropy sorting ideas. Okay, so here's sort of an example of a sort of more modern study of explodability. And so basically the idea is instead of the old Woosley model, where you just put 10 to the 51 ergs of energy into the center and see what happens, What you basically do is you tune the luminosity so that you can get something like 87A to work, neutrino luminosity. Okay, so it might not be the real neutrino luminosity, but then you actually try to use something roughly driven by the neutrino mechanism to explode the stars, where you've fudged somehow on how you've set that luminosity for whatever dimensionality does for it. And so here's the sort of outcome pattern you get. So blue is things which explode, gray are things which don't explode. Okay? And then the explosion energy is the difference between those lines and those lines. And so you can see there's a complicated pattern of how much energy you have in the explosion, and these complicated isolated distributions of things which succeed or don't succeed. So in fact, it's sort of funny is for those of you who are into LIGO and all these population synthesis models, they basically all use ideas about who explodes and who doesn't explode that are 20 years old. Right? No one would use the model that everything above whatever 40 solar masses becomes a black hole anymore, who actually works on the explodability of stars. You'll notice there's nothing down here. It's somewhat amusing that most of the supernova are between 8, 9, 10 solar masses, just because the IMF is steep. No one ever actually explodes those stars because the progenitors are impossible to produce. They have very complicated dynamical burning processes that basically take any stellar evolution code and grind it to a halt. And so no one ever bothers to do those. Okay, so as I said, most of these are low mass. So 27, a quarter of all of them are from 8 to 10 solar masses. All right? 30% from 10 to 15, 15% from 15 to 20, and so forth. And probably everything below 15-ish explodes without too much trouble. Okay? And then the question really is what you're going to do with the half which are above that mass. And as Avi says, there's this whole question of basically all of these massive